Hello, welcome to our lecture on deep learning. Today we'll go back to convolutional neural networks. We will discuss more advanced convolutional neural network architectures for image classification that happened after the LeNet architecture that we have discussed so far. We'll use this architecture to discuss common building blocks and architectural components of these neural networks. So let's dive right into it. At the time when LeNet was developed in 1990, it achieved good results on small images, such as these handwritten digits. So it was used to classify for an image of a digit, which digit was in the image. However, it had yet to be shown that convolutional neural networks were also applicable to larger and more realistic image datasets, and were also able to achieve state-of-the-art results there. At that time, it was largely traditional machine learning algorithms such as support vector machines that worked on handcrafted features that had been extracted from these images and then plugged into these machine learning algorithms, these classification algorithms that were considered to be state-of-the-art. So most of the engineering effort was actually put into the feature extraction, so to craft manually better features to extract from these images that would give you better classification results. So in contrast to neural networks, which can be considered to be end-to-end classification systems, so that take as input the images and then through a series of neural network transformation extract features from these images, these classical pipelines looked more as follows. So first, they obtained an interesting data set. For example, data sets that used expensive 1 megapixel cameras to get images. Then you would pre-process this data set. So you would extract handcrafted features based on knowledge of optics, geometry, or other analytic tools. And then you would feed this data through a standard set of feature extractors such as scale invariant feature transform, also SIFT, or SURF, which was the speeded up robust features, or any number of other hand-tuned feature extraction pipelines. And then these resulting representations would then be used to plug into your favorite classification algorithm. So it's a classification algorithm that takes a feature vector, namely those features extracted from the images, and then outputs a classification result. And this could, for example, be a linear model or a kernel classifier also. The progress in neural networks was largely driven by a computer vision challenge, the so-called ImageNet challenge. And each of those neural networks that we will talk about today were at some point the winners in this challenge. Neural net researchers believed that state-of-the-art results should be achieved by extracting features directly from the image. And these features, they should be learned instead of handcrafted. And it was in 2012 when Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton developed a convolutional neural network which achieved excellent performance in ImageNet. The neural network is called AlexNet that they developed, where Alex is the first name of the first author of this paper. This neural network did exactly this. It extracted features directly from the image using a series of convolutional neural network layers, where the lowest layers detected things like edges, colors, or textures in the images. And then the higher layers in the neural network would build upon these early layer representations to represent larger structures in the images, such as eyes, noses, grass, or anything else. And then Even higher layers in the neural network architecture would represent whole objects, such as whole people, an airplane, dogs, or a frisbee. Ultimately, the final hidden layer would learn a compact representation of the image which summarizes the content, such as the different classes that could be then separated easily. And here on the right side we see a visualization of image filters that are learned by the first layer of AlexNet. So here you see, for example, a number of edge detectors, so for diagonal edges, or horizontal edges, vertical edges, and so on. You see filters for colors or for color gradients, so for going from one color to another color. It took quite a long time, from 1990 to 2012. So 1990, LeNet, 2012, when AlexNet was developed. And this breakthrough that AlexNet achieved can be attributed to two main factors. The first one was that there was this large data set, namely ImageNet, which was released in 2009, and it had 1 million examples where you had 1,000 images from each of 1,000 different classes. It was the researcher Fei Li who leveraged Google image search to pre-filter these large candidate sets of images for each of those 1,000 categories, and then used Amazon Mechanical Turk, so click workers, to crowdsource the labeling of the images. So that was the first component. The second thing that contributed to the breakthrough is related to the fact that deep learning requires a lot of compute. And at the time, graphical processing units were shown to be a game changer in enabling massively parallel computing. And it was Alex Krzyzewski and Ilya Skutskeva who implemented a deep convolutional neural network that could run on GPU hardware. And this, of course, was AlexNet. So AlexNet was an 8-layer convolutional neural network. And due to the limited memory of these early GPUs, the original AlexNet used a dual data stream design such that 2 GPUs could store and compute half of the model. And you have to imagine that this was implemented from scratch, so they couldn't use all of these convenient software tools and packages that we have access to today. AlexNet won the ImageNet large-scale visual recognition challenge by a huge margin in 2012. So if we look at this 8-layer neural network, on the left we have LeNet, on the right hand we have AlexNet. So in LeNet, the images were really small, they were 28 by 28 in resolution. And then it was passed through these 5 layers. AlexNet is an 8-layer convolutional neural network. So we have a convolutional layer followed by pooling, the second convolutional layer, again followed by pooling, third, fourth, fifth convolutional layer, followed by pooling, and then 3 fully connected layers, summing up to 8 neural network layers. While LeNet used a sigmoid activation function, this was changed in AlexNet to the rectified linear unit. So the rectified linear unit, so if you have here the sigmoid, that goes from -1 to 1, the tanh function. Here you have the 0. The rectified linear unit instead looks like this. So it is 0 for negative values and than the identity for positive values, which is much simpler and faster to implement. And it avoids the vanishing gradient problem that you have in the tanh function when you're here in these regions of the sigmoid where the derivative is equal to 0. AlexNet also introduced a regularizer to the fully connected layer, namely dropout, where LeNet only uses regular weight decay. In dropout, you randomly in each iteration sample a subset of the parameter and set them to 0, thus dropping them essentially out from the network. So you're dropping a random fraction of your neurons. So to summarize, AlexNet has a similar architecture to LeNet. However, it uses slightly more convolutional layers, also has a larger input size and a larger parameter space that could fit to large-scale data such as ImageNet. Today, AlexNet has long been surpassed by much more effective architectures, but it is still a key step from these shallow to deep neural networks that are used today. Although it seems that there are only a few more lines in AlexNet's implementation than in LeNet, it took the academic community many years to embrace this conceptual change and take advantage of the excellent experimental results in AlexNet. This was also due to the lack of these efficient computational tools that we have access to today. Dropout, the ReLU, and preprocessing were the other key steps in achieving excellent performance in computer vision tasks. During the further development of convolutional neural network, the designs of these architectures has grown progressively more abstract, where the thinking has moved from individual neurons to using layers and now to blocks as repeating patterns of layers. So the idea of using blocks has emerged from the visual geometry group, in parentheses VGG, at Oxford University. Their so-called VGG network used blocks as repeated structures that were implemented using loops and subroutines. The VGG network consists of two parts. The one are 5 convolutional blocks and the other one are fully connected layers. Here we see a comparison of AlexNet with its convolutional layers and a single block of the VGG. So a VGG block is a number of convolutional neural networks that are then followed by a single pooling operation, where the pooling operation achieves a spatial downsampling of the output of the block compared to its input. The first block in VGG has 64 output channels, and each subsequent block doubles the number of output channels until this number reaches 512. In their paper, Simonian and Zisserman employed convolutions with 3x3 kernels and 2x2 max pooling with a stride of 2, which halved the resolution after each block. The second component are 3 fully connected layers, which is similar to the structure of AlexNet. As the VGG network uses a total of 8 convolutional layers and 3 fully connected layers, it's also known as VGG 11. To summarize, VGG 11 constructed a network using reusable convolutional blocks. Different VGG models can be defined by the differences in the number of convolutional layers and output channels in each block. The use of these blocks leads to a very compact representation of the overall network definition. And it allows for efficient design of very complex neural network structures. In their original work, the authors Simonian and Sisserman experimented with various different architectures. In particular, they found that several layers of more deep and narrow convolutions, for example 3x3, were more effective than fewer layers of wider convolutions. LeNet, AlexNet and VGG all share a common design pattern, namely they extract features that exploit the spatial structure via a sequence of convolutions and pooling operations. Then they post-process these representations via a small number of fully connected layers. And the improvements upon these networks and over the original LeNet mainly lie in how later networks widen and deepen all of these modules. Alternatively, you could also imagine using fully connected layers earlier in the neural network. However, the problem is that dense layers would give up the spatial structure of the representation entirely. And the so-called network-in-network block, or NIN block, offers an alternative that keeps the spatial structure using one-by-one convolutions. These network-in-network blocks were proposed by Lin, Chen and Yan in 2013 based on a very simple insight, namely that a one-by-one convolution corresponds to using a multi-layer perceptron on the channels for each pixel separately. If we look at a network-in-network block, then we see that it first applies a normal convolutional layer and then two one-by-one convolutions. And what one-by-one convolutions essentially are doing is that they are applying a dense layer to a single pixel in the representation that is output by the convolutional layer. And they do it for every single of these pixels. And then the output and the input are basically of the same spatial dimensions with a possibly changed number of channels. So each element in the spatial dimension, so in height and width, can be interpreted as an example and the channel as the equivalent of a feature of this example that are then plugged into a fully connected neural network. The NIN network also uses ReLU activations. And the neural network then corresponds to a number of these NIN blocks that are then followed each time by a pooling operation. So you have an NIN block followed by a pool, another NIN block, another pool, NIN block, pool, NIN block. In the end, instead of employing fully connected layers, the NIN uses a global average pool across the spatial dimensions, reducing the tensor that is height times width times number of channels to a vector of size equal to the number of channels. And this is then used for the classification purpose. By doing this global average pool, the NIN avoids dense connections altogether by introducing a number of output channels that are equal to the number of class labels. So then you can apply a softmax to this resulting vector and you get your class probabilities. The advantage of this approach is that it significantly reduces the number of parameters comparing to a dense layer at the end. To summarize, NIN uses blocks that consist of a convolutional layer followed by multiple 1x1 convolutional layers. This block can then be used within the computational stack to allow for more per pixel nonlinearity than the convolutional layer alone. NAN completely removes any fully connected layers and replaces them with a global average pooling in the end. So which means that you're essentially summing over all the spatial dimensions, and you apply this after you've already reduced the number of channels to be exactly equal to the number of output classes. So you have your height times width times number output class tensor, and you're averaging across height and width to arrive at a vector that is equal to the number of output classes only, which then yields your logits that then go into your softmax. By removing any dense layers, it reduces the number of overfitting as it has dramatically fewer parameters. And the design has influenced many subsequent convolutional neural network designs. In 2014, Szegedi et al. Won the ImageNet challenge with a structure that combined the strength of network in a network and repeated block paradigms. One focus of that paper was to address the question of which sized convolutional kernels are now the best. So after all, if we look at previous popular networks, they employed choices as small as 1x1 convolutions up to 11x11 convolutions. And one insight in this particular paper that we'll discuss next was that it can be advantageous to employ a combination of variously sized kernels. The resulting network is called Convolutional, and it employs the so-called inception block, which is likely named due to the quote, "We need to go deeper from the movie Inception." If we look at this block, it takes an input and then it employs convolutions of different sizes, namely a 1x1 convolution, in parallel a 1x1 convolution followed by a 3x3 convolution, in parallel another 1x1 convolution followed by a 5x5 convolution, and a fourth parallel 3x3 max pool followed by a 1x1 convolution. And now all of these 4 parallel computations are then concatenated into a single representation. So the first 3 paths of the inception block use convolutional layers with the window sizes of 1x1, 3x3 and 5x5 to extract information of different spatial sizes. And the middle 2 paths perform a 1x1 convolution on the input to reduce the number of input channels and to reduce the model complexity. The fourth path uses a 3x3 maximum pooling layer followed by a 1x1 convolution to change the number of channels. The 4 paths all use appropriate padding such that the input and output have the same height and the width. And finally, all of these outputs are concatenated along the channel dimension and comprise the output of the whole inception block. So intuitively, by having multiple features at multiple different sizes, you are exploring your image for details at different ranges. And so you have some for more short range, but you still want to also not ignore the longer range entirely. If you look at the complete Convolutional architecture, it consists of 9 of these inception blocks. 2, 7, 9, and has in between max pool operations. At the end also has a global average pool operation, and in the beginning it uses pooling, a 1-by-1 convolution, then a convolutional layer with a 3-by-3 convolution followed by a max pool. So the first part is identical to how it would be in AlexNet or LUNET, and then it employs these newly introduced inception blocks. So to summarize, an inception block is equivalent to having a subnetwork with 4 different paths that in parallel extract information through convolutional layers that have different window shapes and maximum pooling layers, where 1-by-1 convolutions reduce channel dimensionality on a per pixel level and max pooling reduces their resolution. The whole Google LUNET connects multiple of these well-designed inception blocks with other layers in a series, where the inception blocks for Google LUNET were trained on a large set of experiments on ImageNet. Google LUNET, as well as its succeeding versions, were one of the more efficient models on ImageNet, providing similar test accuracy with lower computational complexity. And with this summary, I want to say thank you and goodbye, and see you in the next lecture. Bye-bye.